systems of equations, so we're kind of, again, going in that backward pattern of looking at things. We want to understand the geometry of three equations with three variables. We want to be able to solve them by elimination, and we want to be able to solve systems that have some missing terms, and then we have some special systems. Once again, desmos.com is helpful, but when you have three equations, it can be slightly more difficult to be able to generate the graphs and really understand what's happening there. So it's not your best option when we have three variables. I will be providing a matrix calculator to assist you with this, so you can work with the matrix methods, but be utilizing a calculator to help you. So the ordered pair for the intersection of three variables is called an ordered triple because there are three values in the point. A graph of a linear equation with three variables is a plane. So what does that mean? It means we are actually graphing a rectangular piece of information. So we're in 3 dimensions, not in 2 dimensions. The number of possible solutions are a lot. So it could have a single solution, points of a line in common. We could have all these different geometric understandings of how the planes intersect. Do I expect you to be able to draw this or to be able to look at a problem and tell me this? No. But I do want to take the time to explain this is how the planes would intersect one another when you're given the equation. So the common situation is the planes are going to meet at a single common point, or they're going to have points of a line in common. So that would be back in the image here. We have points in line in common or a single point. That's what we're focusing on here are these two cases. Case 3, the three planes may coincide, and in that case, the solution is all the points on a particular plane. Then they may have no points in common at all. So that would be like if we had lines that were parallel to one another in a 2x2 system. So the way you're going to do this is you're going to work to solve the linear system by similar methods to what we did with the 2x2 systems. We're going to use what we call a focus variable, and that's the first variable to be eliminated. We want to work smarter, not harder, when we're choosing which variable to eliminate. So we're going to select a variable and an equation to work with. The good choice here is one that has a coefficient of 1 or -1. So we're wanting to work smarter, not harder. We're looking for that key characteristic. Then we're going to select an equation that contains the focus variable as our working equation. We're going to work to eliminate that variable and then eliminate the focus variable again so that we have a clear system of equations to solve. And we're going to write the equation in 2 variables. So basically what we are trying to do is take an equation with 3 variables. I want to be able to eliminate the third variable so it's something I know how to do. So what does this actually look like in action? This is where those steps can be very confusing because you're not seeing them happen. So if I wanted to solve this 3x3 system, I would choose the working variable as y because I have 1, a -1, and a +2. And I would choose the y because the first and the second equation are going to cancel out. So if I add equations 1 and 2 together, this gives me a new equation, which I'm going to call equation 4. So that y canceled, I just have x and z. Now I'm going to use the working equation, which I chose as 1, to cancel out with 3. And I'm going to call that equation 5. What I'm going to do then is I'm going to put 4 and 5 together, and then I'm going to solve it like a 2x2. I'm going to add them together so z is canceled out, so I get that x equals -1. Once I know that x equals -1, I can substitute back in 4, not the original equations, back in 4, and that gives me z is 2. Now that I know x and z, I can plug it back into the working equation number 1. This is a lot of steps. Pause the video, rewind it, and take a second watch on it. So what it appears like is because I got one singular point that is the only solution of the problem. We can then check our answer by plugging it in to make sure it works in all 3 equations. When some equations have missing terms, it's kind of nice because then I don't have a pure 3x3. Since equation 3 is missing a y, I can eliminate the y again from question 1 and 2. So if I multiply question 1 by 2, and I add that to number 2, so that's what I would generate, I'm going to get equation 4, which has just x and z. Then I'm going to use 4 with 3 to eliminate the x value and solve that 2 by 2. So I don't have to get two separate equations here. I'm able to just do it in one because I don't have the y variable. So I get z equals 1. Then I'm going to take that z and plug it into one of my made equations to get y is negative 2. Now that I have z and y, I will plug back into my working equation, which is 1, with those values to find x. Special systems. What do special systems look like? When I solve the system, and I'm going to go through this quickly because the examples I gave on the previous slides are the better ones to look at when solving the equation. If I look at this, they're all multiples of one another. So my solution set is going to be that first equation. So take a minute and look at that. If I multiply the first equation by negative 3, that gives me the second equation. If I multiply the first equation by 2, that gives me the bottom equation. So that means that this entire solution set is that lowest value equation. And this equation, the relationship is not quite as apparent. So what I'm going to do is I'm going to multiply equation 1 by 2 and add it to 3 so that I can eliminate it down to a 2 by 2 variable. As I'm working through the process, I say, oh wait, I get 0 equals 7, which is not true. Right here I know there is no solution to this equation, to this 3 by 3. What I would do here is work it like normal, and what I would do is different from the book. I would actually multiply the second equation by 4 to clear out those fractions, and then I would multiply the bottom one by 2 to clear out those fractions. So that then I have a workable 3 by 3, and what I notice here is I have the same equations with one main difference. So what does that actually mean? Equation 1 and equation 2 are the same, so they have the same graph. Equation 3 is not the same because I have negative 12 instead of 8. So once again, I have no solution.